Hello, gentlemen. This is kind of a common memory leak / crash in C++. Um, it has to do with vectors, classes that have pointer member variables dynamically allocated. It's kind of a problem of, what's it called? It's a problem of pointer ownership or memory ownership. You'll see what I'm talking about. Int main, we got the spill function, then we pause and return. In the spill function, we create a vector of class leak with 10 million elements, and we construct this right here, this temporary, and then we return nothing. The leak class in the constructor has a constructor right here that just allocates a new int between 0 and 255. Right here, our int is a null pointer. In the destructor, we just check if we have a null pointer, and then we delete it and set it to null pointer. Pretty simple. Now, if you know anything about C++, you should get a feeling that this is going to crash. You'll see. Of course, it did. Why did that happen? Heap invalid address specified to RT-validate heap. So some type of heap corruption, accessing memory we weren't supposed to access. Who knows, right? Let's put a breakpoint here at the return. Let's check if we even get to the return. And let's check what's going on here. So we make it to the return. That means we crash right after the return. So the spill function completes as far as getting to the return. Obviously, this is not crashing the program. So between the return and here, that's when we're crashing. Let's look at the contents of vec, our vector. 10 million elements. Okay, so we have this B000 memory address that's in every single one of our objects. And the int is -57. So they were supposed to be set between 0 and 255. It's clearly not the case. -57, it's not what we wanted. And the memory address is the same for all of them. Okay, so why is that happening? Well, this leak isn't temporary. So whenever we constructed this here, it gave us this B000 memory address, and it gave us some value between 0 and 255, right? So whatever was at B000 was between 0 and 255. And unfortunately, writing the call like this or constructing the vector like this, we just copied this temporary 10 million times exactly into the vector. So we didn't create, we didn't call the constructor for this leak class 10 million times. We just called it once and then copied it essentially. Another thing that's going on is because this is a temporary, once we pass this line, this temporary is going to have the destructor called. And guess what? Since this temporary contains the B000 memory address, once we run this constructor, whatever is sitting there is going to be deleted. So we don't have a value. It's sitting at -57 when it should be between 0 and 255. So this memory address was already deleted. And now we have a vector of 10 million classes containing this memory address because they were not set to null pointer because they were copied before the destructor even ran on this leak temporary. So what happens when we get out of the scope on this void function is that the vector is going to be destroyed. So let's continue. Let's just step into right here. Yep. Now we get to the destructor. We see that we're going to try to call delete on this B000 address, which we already called delete on, and you can tell because this -57 value. And yeah, that's where we crash. Okay. So clearly this can't be a temporary. Let's just, maybe put it up here. Leak L. And let's just pass in L here. So this is also going to crash, right? So it's not a temporary, so it's not being destroyed. But unfortunately, once we leave the function, this leak, you know, is still part of this function, so it's going to be destroyed. It doesn't make any difference whether we put it out here as well. That doesn't make any difference. Reason being, since these are all still copies of L, they all have the same memory address. So whenever, let's say the vector goes out of scope, the first element in the array calls a destructor, and the second element calls a destructor. Well, they both contain the same memory address because they're both copies of this leak L right here. Okay. Now, clearly, we can't have these all be copies of leak L. So instead of having them as copies of leak L, let's just, you know, get a vector of 10 million elements. Let's write a for loop for autoref j in back. Let's say that essentially L dot I, and I guess we're going to have to construct a new int. Right, so this is already kind of nasty. And then we got to say that, I guess, j equals I, right? No, not I. For auto L, j equals L, yeah. Okay, let's see. Does this crash? Okay, it still crashes. Of course it does. The reason is, well, let me set this instead of 10 million elements. Let me set this to 10 elements. And let's put a breakpoint at this return. So we're going to make it to the return. Okay, let's see what the issue is. So our memory address is 6, let's just say 3D9, right? And then our final element has the memory address 3D9. Yep, both values are 135. So whenever L goes out of scope and then vector goes out of scope, well, the destructor is called on the same memory address twice. And that's where we get our crash. Okay. So we don't want leak to actually hold any memory address. So now we're going to do something really nasty. L dot leak destructor called. We're going to explicitly call the destructor on the leak. And now, since these are well, I guess actually before we do this, this is something I was going to demonstrate later. So what's it called? First and foremost, let's actually just set L.I to null pointer so that it's not going to delete that memory address, right? The final element in the array is going to delete the memory address. L is just going to be kind of turned into an empty shell by setting its pointer to null pointer. Right, so we kind of did like a pseudo kind of move semantics type thing. It looks really nasty. Let's see if we get a crash. Nope, no crash. But that doesn't mean it's without issues. If I launch the program, okay, we are sitting here holding 650 megs in the RAM. Let me actually set this to release. I'm just going to build it. And let's go find it. So basically, I'm going to consult task manager, see how much memory we're leaking. So this is just sitting on the pause Yeah, 160 megs of RAM. That shouldn't really be happening. So clearly there's some RAM being leaked. Why is it being leaked? Well, whenever we construct this vector, these 10 million elements are still kind of constructed, right? So, and since when they're constructed, they all allocate a new int. They, what's it called? Those ints are all overwritten down here, but they're not deleted. And so they're all basically just floating around in memory. Okay, so now we have to explicitly call, before we do anything in here, j.leak. So we can explicitly call the destructor. Now this is getting really nasty already, but let's just run this in release. You'll see right here, it drops down in Visual Studio to 2 megs, so it's not leaking any memory anymore. Okay. There's kind of an alternative that we can do instead of this. What if, well, let me point out this problem. We actually have another memory leak because before we ever call the destructor, or right here when we construct this L variable, we call the constructor, but we never call the destructor because before it ever goes out of scope, we overwrite it right over here. So this is actually a memory leak as well. So we should explicitly call the destructor on L. Okay. Alrighty. So now this is nice. But actually this gives us a slightly better solution. We can get rid of this memory leak right here. So just pass in L. Since L has already ran the destructor, L is just kind of an empty shell variable. So now we're constructing 10 million empty shell classes inside of here. And then L still has to be set to null pointer at the end because it's being set right here. Yeah. So it should be no memory leak. And yep. So no memory leak from this little variable L. No memory leak from this vector. But this is truly disgusting. Now you could try and do something like, what if we had an init function, right? And so init just basically did the work of the constructor. And it's got to be void. And let's get rid of our constructor because it wasn't really doing well for us. And I guess here, so we don't have to have this temporary L anymore. Let's get rid of it. Right, and then I guess basically, yeah, for every item in vector, let us just, what's it called? Call the init function. So, j.init, right? And so we should have something a little bit better going on here. I don't want to run this in release. Yeah, let me change this back to debug. Okie dokie. I'm just double checking. Is this a memory leak? I'm just trying to... No. This is not a memory leak, right? Yeah, I think we're chilling. Yeah, no memory leak. Okay, no memory leak. Let me put this back here, double check that all our values are correct. So yeah, they're all, you know, unique values and unique memory addresses. So no issues here. This init function works well. Okay, but we just gave up our constructor. So let's get back our constructor because this is truly disgusting to do this. I mean, imagine if you were using another class and you couldn't do all this garbage that we're doing here, right? So let's get rid of this. We got our constructor back. And we're going to have to make a new constructor right here. It's going to be the, oh, this should be our constructor. We should make a copy constructor. So let's make a copy constructor. Leak. Const leak ref. Let's call it L. Why not? And in a copy constructor, what you should do is, since this is a class that manages what's it called? Yeah, since this is a class that manages its own memory, right? It's got ownership of this pointer right here. In this copy constructor, you should give it allocate new memory for it. So essentially we're going to say I equals new int, but instead of doing that, we are going to say L dot I and get the value of that. So we are constructing in the copy constructor we're passing in a leak, and then we are constructing essentially a new class with a new pointer with whatever the value inside the previous class is. So we don't have that init function anymore. Let's try to go back to our original function right here, our original delio. Okay, so we got this temporary again. Let's check if this is going to crash or if this is going to give us any issues. Okay, so it doesn't crash. Let us see. Okay, so we have all unique memory addresses. Why? Because whenever this temporary is passed in here, we're not passing it to this new constructor up here. We're passing it to this constructor right here. Because it's being copy constructed instead of default constructed. And so normally the compiler actually generates you a default copy constructor. So the copy constructor that the compiler generates actually doesn't have this code. The compiler actually writes this in the copy constructor. I equals L.I. And so it doesn't allocate any new memory for you. It just points your pointer to the memory address of the other pointer. So previously, that's why we had all of the memory addresses the same when we tried this method earlier in the video. Now all the memory addresses are new, but they are the same int. So clearly this doesn't work either. Let's get rid of this. Okay. Now, what is the point of default constructing all of these vectors or all of these elements in this vector? Because we're going to have to destroy them later, right? So let's just create a vector that's empty. Then let's do vec.reserve. 10 million. Right, and so now we got to run our for loop. I pressed L instead of semicolon. And I guess let's just write vec.pushback and give it a newly constructed leak, right? Okay. This is also an issue, but you know, we'll see later why. So let's check if there's any crashes, if there's any memory leaks. Okay, no memory leaks, no crashes. Let's check if all our values are correct. Right here. Okay, so we have all unique memory addresses, all unique values, so everything looks to be good, but there's still an issue. The issue is that every single time we construct this temporary, we're constructing this temporary 10 million times. Every single time we do that, it's going to allocate an int right here. It's going to run this constructor, and then it's going to run this copy constructor to construct the element inside of the vector. So the vector is going to get an object that's created from this newly created temporary object that we're creating 10 million times. So we're getting 20 million calls, 10 million calls of this, and then 10 million calls of this. So clearly something's not right. Now what you can do is actually first I'll just show you that since we got a copy constructor, we should actually make a copy assignment operator. So to make a copy assignment operator, all I'm going to do is return a leak reference, and then operator equals, and then we are going to take, const leak ref L and do that with it. So now we have a copy assignment operator. So if we were in our code at some point basically to say leak L, leak Y, L equals Y, well then Y would not equal L, and that's what you want, because Y is going to have a different memory address for its data than L, because our copy assignment operator dictates that. The reason we want that is because whenever L goes out of scope or Y goes out of scope, we don't want them deleting the memory for each other, right? So you can get kind of weird behavior where, L equals Y, but L does not double equal Y. This is not true. This will not return true. Dang, look at that. I can't find the operator. Yeah, but this is not true. But this is true. Okay. Now, we wrote our copy assignment operator, but this doesn't solve the problem here of the 20 million calls to our two constructors right here. We're going to actually add some more constructors. So we're going to add a move constructor. So it's going to be a leak ref L, and in the move constructor you should declare it no except. In the move constructor, basically what you're going to do is say that I equals L.I. So you're doing a basic copy, and then you're saying L.I equals null pointer. So all you're doing is you are taking ownership of the pointer that is in the class that you pass in. So whenever you pass in a class by r-value reference, you are going to take in the ownership of that pointer. Anything that's r-value or anything that's r-value reference, essentially. So you can cast things to r-value reference, of course. But for example, now we can look back at this code and see that this is a temporary. And so whenever this function gets called, we are going to be moving instead of copying. And there you go, still works, no memory leak. And how do we check if it's moving? Well, I'm just going to throw a debug message in here, I guess. And we should see that on our console. Are we moving? Of course. Now we're moving it. That means we are avoiding new memory allocation. We are not going to allocate memory twice. Right here and right here. We're going to allocate memory once, and then we move it. Now, this is not perfect because we're still getting 20 million function calls. Get this function call, and we are getting this function call. But the compiler probably optimizes it away anyway. Now that you got a move operator, you want a move assignment operator. Right here, we are going to be saying that we return a leak ref, and that the operator just looks like this. Yeah, I mean, that's essentially it for the move assignment operator, right? Isn't it? Should just do the same thing as the move constructor. So yeah, now if we do the same thing here, where leak L and leak Y. Now if we do L equals Y, we're going to call the copy constructor. Where is it? Yeah, right. Oh no, I'm getting confused. Copy assignment. And down here, move assignment. So if we run this, must return a value. Oh yeah. What am I doing here? Gotta return this. And down here. Okay, so we get a copy assignment. Now, if we do standard move, we get a move assignment. Now, wait, why do we have to use standard move right here, but we don't use standard move right here? Look, this should get a move assignment. Or if, I mean, I'm just going to take this and put it in the move constructor, right? We're going to see that we're going to get a lot of move assignments, despite the fact that we're not using standard move right here on this vector pushback. Okay, the reason we're using the move operator or the move constructor is because this is a temporary. So temporaries will automatically pick move constructors. So if we wanted to actually use a move constructor here without using standard move, you can just get rid of this leak Y, and you can just say that L equals a leak. And let's uncomment this. Let's get rid of this. Move assignment. So you can see we got a move assignment without using standard move because this is a temporary. It does not have a name. Okay. That's all well and good. But we are still calling, you know, this function 20 million times, right? And we're calling this constructor, And then we are still calling the move constructor. So that's 10 million calls of each. That's 20 million calls. And look at how many constructors you got to have in C++ these days. I mean, what is this? This is crazy. Okay. You're still calling the move constructor 20 million, or the two constructors 20 million times. Here's something I just want to show you that's kind of funny. Since this is a temporary, of course, if you wanted to call the copy constructor, all you got to do is make a temporary. So leak L, and then push back leak. And this is gonna obviously call the copy constructor. It's not telling us because I don't have any debug, but yeah, that'll call the copy constructor. And if I do standard move on this, now it is going to call the move constructor. So let's time it. Let's see how long it takes. So I guess let's say standard chrono, high resolution clock, and let's just say that auto n equals clock dot now yeah, and I guess let's see out the time it takes. Standard chrono. Milliseconds. And not that. We don't want to assign that to a function. We want to assign that to the result of the function. N, or no, let's do dot now minus n, right? And that should be that, I think. Blah, blah, blah. Type 2 where there's no acceptable conversion. Dot. Okay, 1592 milliseconds. And that's if we move it. So let's unmove it. Let's just copy it. $31.05 milliseconds. Okay, let's actually double this up so that we can check it back to back. Maybe it's run variance. Let's make a second vector. And let's get rid of this code. This code is useless for now. Vec2 dot pushback. Let's just make a temporary right here. Yep. Standard C out. vec2. Vec2 is undefined, of course. Okie dokie. Yep, I think that looks good to me. Vec2.pushback. Let us run at the end of this return to double check that we got good values in all of them. Nothing's messed up. So 31, 38, and 1540. So half the time for the move. Let's see if we got good values. Make sure we're running this while. Yep, so that looks good to me. Yep, both of them seem to work good. Okie dokie, let's also run this in release mode so that we can actually benchmark it. Okay, so it's actually still faster in release. Release did not optimize away the double construction, I guess. Here is some magic that you can actually do. So this looks a little bit more elegant. It's in one line as opposed to two lines right here. So what if I didn't want to create that and I just wanted to pass this into the copy constructor explicitly? How do I do that? There's almost no reason that you would ever want to do that, but you can create a temporary, copy it with the copy constructor, and immediately destroy it because it's a temporary. Obviously, it's going to be destroyed right afterwards. So you just got to do a const cast to a, I guess, a leak ref, and you just got to put in your leak in there. I think that should be that. Expression must be an L value. No, it doesn't care. This is C++. There you go. Compiles even with the error message. I mean, like, that's pretty funny. I tried other methods to forcefully use the copy operator or the copy constructor on a temporary, but this is the only way that I got working. Kind of funny. Don't write code like this. This is magic code. This is not code that anybody should write. But yeah, you can see this one runs the copy and this one runs the move. Pretty clearly. Now that they're timed, you know, we finally got this move, right? And we finally got this copy working. Now, what if I told you all of this was not the best method? What if I told you that instead of, you know, playing with all these shenanigans, all you were supposed to do is vec.inplaceVac and that's it. Let's check the timing. 1500, 1600. They're the same speed, let's just say. It's essentially no extra work to run the copy constructor. But here, or the move constructor, I meant to say. Here, we're only running 10 million calls because we're actually constructing the objects in place. We are only running this constructor up here. All the rest of these constructors are worthless. Down here, when we pass this, we are creating this temporary. So we run this default constructor. Then we run this move constructor. Now you can say they're essentially the same speed, but I mean, still, look at this. And I can, let's verify that this doesn't run any of the constructors. So I'll put some debug messages in each of the constructors. COUT. Let's call this the copy constructor. Let's call this copy assignment. call this one a move constructor. Let's call this one a move assignment. And I guess let's call this one a default. And let's see, it prints default. Let's get rid of this just so we can see what the second one prints. Move. Are we getting any calls of the default constructor? I actually have no idea why I didn't see. Oh, it should actually have a call of the default constructor. But I just removed the debug message. Obviously, we're not going to see default. And let's get rid of this. Now we're going to see that we're getting default and move. It says default move. I mean, look at that. Default move. Default move. It's calling the default and move constructor. So we're getting twice as many calls. There we go. Let's get rid of all these debug messages. And let us finally test this. So we got the move and we got the construct in place. Now the reason we're not passing anything into here is if I pass in for example, a temporary, well, this is exactly the same as push back, because in place back will call the constructor as if whatever parameters that you pass in are the parameters that you're passing into the constructor. So because we're passing in a leak temporary, it's going to find whatever constructor will construct a leak class using a leak temporary. So it's going to call the move constructor right here. Let's prove that actually, just to show you. And let's comment out this. We are getting the move constructor called. Now, if we remove this temporary, we are getting no move constructor called. So what is happening here? Well, in place back will construct. It's just as if you were constructing the object with whatever parameters that you're placing into in place back here. So if I place a temporary in here, it's going to find a constructor that takes a temporary, which is this move constructor. If I place an L value in there, it's going to use the copy constructor. If I place nothing in there, well, which one of these takes nothing? The default constructor takes nothing. So it's going to use the default constructor. And so if I make a temporary here, I am going to call the default constructor to construct this temporary in place right here. And then I'm going to go up here and call the move constructor. So when you're using in place back, do not pass it a temporary, do not pass it an L value, just pass it whatever parameters are used for the constructor that you're trying to call, essentially. Okay. Now that we have all that, let's throw this in release and let's benchmark it for good. That's not going to be a good benchmark. Okay, 394, 398, 401, 395, 395, 395. So you can see they're essentially the same. Maybe it's a little faster. No, maybe it's a little slower. Maybe it's a little faster. If I had to bet on one being faster, I would essentially say that this in place back is faster, because we're only calling the function, we're calling half as many functions as this loop down here. But this just kind of shows off how fast move semantics are since they're so close. Anyway, gentlemen, that is all. Pay attention to your ownership of your pointers. Pay attention to which constructors are being called in your classes. And benchmark, I guess, as well. Bye-bye.